So let's recap some stuff that we talked about with circular motion, specifically in terms of the equations. Okay, so circular motion. And when I say circular motion, folks, I do mean uniform circular motion. Actually, we'll just say circular motion. So we know that the average speed for an object going around in a circle, and we'll call it VT for the tangential speed, tangent to the circle, 2 pi r over the period. We also saw that the acceleration that something experiences when it's in circular motion is the radial acceleration, or also called the centripetal acceleration, and that was Vt squared over r. Meaning that when we come back to talk about the net force in the radial direction, that's going to equal MAR, or if we want to write that in a different way, the net force in the radial direction is going to be equal to mvt squared over r. It's a little bit different than we're talking about something that's speeding up or slowing down as it's going along a line. This is the rate at which, remember, the rate at which the direction changes. So we're going to break down what this means a little bit more in just a second. So, because I want to remind us about what the radial direction looks like. If this is my circle, right, the radial direction means along the radial line. Now, as an object moves through a circular path, where it is along the circle changes, right? So the kind of quote-unquote direction of that radial line is changing a little bit. But when we're talking radially, there's two possible directions radially. There's radially inward and there's radially outward, right? So in and out. And so our job when we do these problems is to identify where the circle is and then see what's going radially inwards versus outwards. Because if this is the net force in the radial direction, in the same way if we have net forces in the x direction, we declare one of those directions along x positive, whether it's left or right or up slope, down slope, whatever it is, whatever x-axis is. And we say all the forces in one direction minus all the forces in the other direction. It's the same thing here, except we don't need to make a declaration with the radial axis, because every time you move in a circle, there is a net force inwards. So for the radial direction, we are implicitly going to always have the positive radial direction be inwards. Meaning when we're doing a sum of forces in the radial direction, we're going to take the forces in and then minus out the forces out. And that's going to equal mvt squared over r. Every single time, forces in minus forces out. If there's two forces in, we'd have a plus force, minus nothing. If there's a force in and a force out, it'd be a force minus a force. If there's a force in and two forces out, it'd be a force minus a force minus a force, whatever it is. But that's how this works, right? So from there are two general flavors of circle problems then. There are horizontal circles, okay, and there are vertical circles. So I just want to first start by giving some examples of horizontal circles and vertical circles. Now, let's not get too caught up on the circle part, actually, because as long as you're traveling in a curved path that's a section of a circle, that functions like it's a circle problem because you're going in a circle for some part of a motion. So what's a horizontal circle? An example might be twirling your keys overhead, parallel to the ground. Okay, that's what I had you do in the previous video, where I did that at least. You might have done something different, but I tied a string to my keys and I twirled in a circle over my head such that the plane of the circle was parallel to the ground. Okay, so that might be an example. Another example is a car going around a turn, okay? So when a car goes around a turn, it's going in a section of a horizontal circle. It could be a plane turning as well. in the air at a constant height. That is going in a horizontal circle. So for example, if you've ever been in a plane that has been circling LaGuardia forever and ever and ever, never does that, right? That is going in these horizontal circles, or at least in horizontal circle sections, because it might be going in a circular section and then straight, circular section and straight, right? You know, so there's a lot of different, a person sitting on a merry-go-round. Now, actually, I want to bring something up here. The merry-go-round itself is not moving in a horizontal circle. The merry-go-round as an object is rotating. It's a big metal platform that rotates. But an individual person on the merry-go-round is going around in a circular path. And so we do want to separate out the distinction between a rotating object and an object that's traveling in a circle, right? We only care about objects traveling in a circle. So there are some examples. Vertical circles. The best example, or the easiest, is a roller coaster, right? So when you go through dips and over hills on a roller coaster, you are going through vertical circles. In fact, a lot of amusement park rides use the whole vertical circle thing. Actually, there's a bunch of amusement park rides for horizontal circles, like the Gravitron, you know, the one where you like stick to the wall, or like the Scrambler. That's the one with the 3 carts that kind of go in circles. There you go. So roller coasters, other amusement park rides. It might be like a trick pilot doing loop-de-loops. Right? A loop-de-loop would be a vertical circle. It could just be as simple as swinging a bucket in an arc, or your keys, right? In fact, I'm going to have you do that a little bit later. Swing your keys in a vertical circle, right? So like this. So vertical circle here, meaning the plane of the circle is perpendicular to the ground. Horizontal circle, where the plane of the circle is parallel to the ground. So I'm going to sort of sketch out a sample of problems with each of these, and then we'll get to work with this later in the week. So simple horizontal circle problem, swing the keys overhead. Now, here's the difference with the circle problems. Oftentimes what we want to do is, well, we're going to do a free body diagram. We need to draw some pictures, right? So here, if I'm swinging keys overhead in a horizontal circle, right, I'm just going to draw the keys at one instant. So like, let's say there, right? This would be an overhead view. And I'm going to label my view, because usually what we're doing is something called a side view. I'll show you what this looks like from the side view in, actually, I'll just do that right now. So if I had a side view, this is going to be a terrible picture, folks. I apologize, right? But, right, so here I am. There's my hands holding, well, there's my head holding my keys, and there they go. The keys are going around in that that circle. It's kind of in perspective, right? So the keys are going around like this, and then going around like that. Okay, so let's say this point correlates with that point, or that point at the edge. So first steps, as always. First step is free body diagram. So what forces are acting? Well, on the keys, there's a tension force that acts inwards, right? Because there's a string attached to the keys, right? And it's to the center of the circle there. Now, what other force is acting? Well, the force of gravity is actually acting as well, right? But if you think about it, on this diagram, that would go into the page. I wouldn't really be able to draw that on the overhead view. So when doing this now, and the question is, well, what is the tension in that string? Well, first step, free body diagram. Second step, directionality, right? So I'm going to say, well, inwards is positive R, right? Because I locate the center of the circle. and then positive r's directly into that. Negative r would be directly out. Now the second axis would be perpendicular to the first, so perpendicular to the radius would be the y-axis in this case. Let's say positive y is up. I don't particularly care about that axis right now. So here we go. If I had knowns, I would write those. If there was components, I would do those. I'll talk a little bit more about this in a second in terms of reality. So if I was to write a net force equation now, rather than net F net X or F net Y, I'd write F net R is equal to MAR. We start with the statement of Newton's second law no matter what. Remember, all we're doing is we're replacing this with the sum of forces in that direction, and all I have here is a positive T. Super simple. There's nothing acting radially outward, okay? And that's going to equal M. And remember, we always say, well, should acceleration be something here? Now remember here, because this object is traveling in a circle, the velocity's direction is constantly changing, so the acceleration in question is the centripetal acceleration or the radial acceleration. And there it is. And I can now solve this problem depending on what I know. Right, so like let's say for example, probably the easiest way to do this is I also know that Vt is equal to 2 pi r over the period, right? I also know, let's say if I could sit here and I could measure how long it takes to go around once, and I can measure the radius, then I can find the speed. Once I know that, I just need to do the mass of the keys, and then I can find the tension of the string. But let's see if this physically gels with what you think. The faster and faster I twirl those keys around, the more tense that string becomes, right? So you could physically do that, and when it takes less time to go around, that speed gets larger, that tension gets bigger. And then if you do a long string versus short string, you'll feel the tension being greater for the short string. And I think that makes sense. If you put a more massive object on the end of that string would be more tense as well. So yeah, nice simple problem there. Depending on what you're given now, you can go and solve. Little note about the truth about this. Technically, when you do this, even though the circle is perfectly horizontal, the tension actually acts at an angle, right, to the person holding it. We're going to ignore that for 513 physics, though, because it gets a little complicated, because really what's acting as the centripetal force here, the net force in the radial direction, is the radial component of the tension. But we're not going to deal with that in terms of swinging our string overhead there. But I thought I would just mention that for truth's sake. A second problem is a car going around a corner, right? So here we go, car going around a corner, boom. Right, so here's my overhead view. And here, once again, what we're gonna do is called a back view, meaning if I was standing here looking at it. So in an overhead view, what forces are acting? Well, some force has to be acting towards the center of the circle, and here's the center of the circle, in order to cause this thing to go in a circle. And that force here, in this case, as we discussed in the last video, is static friction. And it better be static friction as long as this thing isn't skidding out. Right, so here, that's that force, static friction, and I've got normal force there, and I've got the force of gravity there, right? And so, once again, axes, that's my positive r-axis, that's my positive r-axis. Notice I don't call it a positive x-axis, because I don't care that it's the x-axis. Yes, it's a horizontal axis, but what's more important here is that it is a radial axis, and my second axis is perpendicular to the first, positive y. And I can write some equations then. If I was going to do a net force in the radial direction equation for here, that'd be positive Fs is equal to mvt squared over r. And if I was to do a sum of forces in the y direction is equal to may, that would just be Fn minus Fg equals may. And ay would go to 0 here because it is not accelerating up or down, so Fn is equal to mg, right? So nothing really changes in terms of our methodology. All that changes here is that we're identifying the radial axis, and the acceleration is known for the radial axis as a separate equation, right? And that's pretty much what all these horizontal circle problems are. And for the horizontal circle problems, identifying multiple views often is really helpful for doing these problems. Next, vertical circles. We're going to talk about two vertical circles. The first is just the keys on the string. So if you have your keys on the string, I just want you to find a safe place there and just twirl them in a vertical circle, right? And what I want you to do is feel the tension as you go around. What I hope you notice when you feel the tension as you go around is that the tension doesn't feel uniform, right? That at one point in the circular motion, the tension feels greater than others. So where is that? Hopefully what you just said is that the tension feels the greatest when the keys are at the lowest point in the string, in the swing, and the tension feels the least when it's at top. And that's very true every time you're in a circular motion like that, that vertical circular motion. So here we go, vertical circle, boom. We're gonna look at two places, the top and the bottom. So when I'm at the bottom there, we have a tension acting upwards and a force of gravity acting downwards. And when I'm at the top, I have a tension acting inwards and a force of gravity acting inwards. And so that's what it looks like for the keys on the string. Actually, let's do the side as well, where I have a force of gravity here and I have a tension there. So there you go. So what does that look like then? Oh, and we did say here that T bottom is greater than T top. That's what our physical experience is going to be. So let's see why T bottom is greater than T top. Well, in each of these cases, we know there's a net force inwards, right? So here's my positive radial direction, and that is the direction of the net force. So if there's a net force inwards, folks, Fg doesn't change as you go around, right? But we know there's got to be a net force inwards. That means that T has to be bigger than Fg. Otherwise, there's no net force inwards. Where that constraint is not true up here at the top. Okay? So just a very quick proof that we know that that's got to be bigger than that. We're going to prove it in other ways as well. So now if I were to do, let's say, a sum of forces equation in the radial direction at each location, F net R is equal to MAR. And then I would notice here at the top, I've got both tension and Fg acting inwards, nothing acting outwards, and then that's equal to mvt squared over R. At the side, I would just have F net R is equal to MAR, and then that would be T, positive T is equal to mvt squared over R. Okay? And then at the bottom, right, F net R is equal to MAR, and that would be positive T minus Fg, because the tension acts inwards, the Fg acts outwards, is equal to mvt squared over R. Notice Fg doesn't belong in this equation because it acts perpendicular to the radius, okay? So if we even look at this, notice here that if the radius mass and the speed are staying the same, here the tension would be equal to this minus that. Here the tension would be equal to just that. And here the tension would be this plus that, once again proving that the tension is greatest at the bottom. Okay, so there you go. So how does that feel at the bottom? Well, hopefully you also said that at the bottom the keys feel heavier. And at the top, the keys feel lighter. Well, that should evoke ideas about fictitious forces. Remember, an object feels heavier when it accelerates upwards, and an object feels lighter when it accelerates downwards. And you'll notice in this case, because the acceleration must be radially inwards, here inwards happens to be upwards. It meets the idea for feeling heavier, and here you feel lighter because inwards is downwards. So there you go. And we can use this for a whole variety of problems. Now, one last thing about this. If I am twirling my keys, right, and I go too slow, right, so do that and go slower, 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 what happens? What you'll notice is the keys no longer make a circle and the rope goes slack, right? So if the rope goes slack, what does that mean from a problem-solving standpoint? Well, that means t goes to 0, right? So what happens here is the minimum speed to go around the circle occurs at the top when t equals 0. Okay, so just as t is equal to 0, for those that are playing along at home, just as t equals 0, yes, if you're thinking, hey, is that a limit as t approaches 0? Yeah, it absolutely is a limit as t approaches 0 at the top. We're not concerned about too slow at the bottom, because if you're too slow at the bottom, it just like sits there. But at the top, if it's too slow, it doesn't work there. So there you go. That's what's going on with the vertical circle with the string. Now, roller coaster. It's very similar, except, folks, there's no tension. So rather than a tension, what do I have? Well, if I look at my cart, and let's say that goes in a loop-to-loop, what forces are acting? Well, I've got Fg downwards, and I've got, instead of t, I've got Fn. Still here, Fg downwards and Fn. And here, because my butt's above my head, Fn pushes down, and Fg is down, right? So there you go. Now, where are the circles? Well, here you go. These things make sections of circles, as I was talking about before. So the curvature of that circle makes a huge difference when practically designing these things. Inwards is always positive. So if I was going to do, let's say this is position 1, F net R at position 1 is equal to M AR. And so that would be inwards, which is positive Fn. I should have been doing magnitudes around all those before, excuse me. Minus outwards, which is the force of gravity, equals mvt squared over r. If I look at position 2 here, F net R2 is equal to MAR. Notice here, even though the free body diagram looks the same, the circle is in a different place. Now, FG acts towards the center, but Fn acts radially outwards from the circle, so it's minus mvt squared over r. And then finally here, F net R3 is equal to MAR. And then here, both Fn and Fg act radially inwards. Okay, so these problems are not that bad, and it's just a matter of what do you know. And we'll talk a lot more on Thursday and Friday about practically doing problems, and we'll do some problems together and look at some of the more interesting applications of what's going on here. But constructing the free body diagrams, and it means just drawing your free body diagrams and being very conscious about where the circle is. That's the key idea. Where is the circle? What goes in, what goes out? And from there, we can do all these problems.